Okay, so welcome back. In the last part, we discussed about the frequency and the wavelength of the X-ray and the uses of the X-rays as well. Now coming the experimental results in that time obtained using the X-ray, we have to understand that result is very, very important. So X-ray, the experimental results of X-ray, why is very important? Because it gives the idea about the atomic number of metal. So that's why it's very, very important. So in that we'll discuss the Moseley's law is very important. What was the experimental setup? We have to always remind that the cathode ray is flowing, and in the trajectory there is a solid. The cathode ray is actually the flow of electrons, which flows in a high velocity moving electron. It actually bombards in the metal surface, and the X-ray is emitting from the metal surface. This is the case, right? So when you see the spectrum of the X-ray of the then you can see there are two kinds of peaks we can say, right? Yes, two kinds of X-ray spectrum. So let me start. This is very, very important. This is the X-ray spectrum. Okay, this is the X-ray spectrum. Now first I have to see what is the X-ray spectrum looks like. So this is the X-ray spectrum obtained during the experiment. So you can see here this is plotted against this wavelength, and this is the relative intensity. So you can see this is the spectrum. Actually there are two peaks. You can see here this is K beta and this is K alpha. Two peaks are there. Otherwise the spectrum is totally continuous spectrum. So it's actually the superposition of two spectrum. This is the continuous spectrum and there are just two peaks. So this result, this is the experimental result obtained during the experiment with the molybdenum metal. So this is experimental result. So now we will discuss this X-ray spectrum, why this spectrum obtained. So there are two kinds of spectrum are there, continuous and the characteristic spectrum of X-ray. So let me draw it first because it's very, very important. Here the wavelength lambda, and here the intensity, relative intensity. How the spectrum look like? Like this kind of. This is our spectrum. Actually this spectrum obtained during the experiment, in the experiment the molybdenum, the metal in the trajectory of cathode ray, that metal was actually molybdenum. Okay, molybdenum was considered and obtained that there is a this kind of two peaks are there. These are two peaks. This was called K beta and K alpha peak, and there is another. So this spectrum actually superimposition of two different spectrum. If you break it, then you obtain one spectrum is like this, plus actually this two spectrum were there. Okay, combining these two spectrum we obtain this superimposed spectrum actually. So this is the X-ray spectrum. Now we have to explain why this spectrum looks like this. This is very important. So this part is called, let me write it, this is called continuous X-ray spectrum, and this is called characteristic X-ray spectrum. Reason behind these two spectrum is very, very different. Okay, so this is actually, again, okay, let me write it, lambda I. Okay, so yes, this is for the molybdenum, right? These peaks, this K alpha and K beta, these peaks actually depends on the metal, which metal you are taking. But this continuous spectra is independent of the nature of metal. Okay, these peaks for the molybdenum, these peaks obtain around 60 or 70 picometer, you can say around 60 or 70 picometer. Picometer means 10 to the power minus 12 meter. Okay, So we have to explain this, right? So first, what is the reason behind this continuous X-ray spectrum? When the X-ray is bombarding in a metal surface, what will happen? We have to understand that first, then it will be very easy, nothing is there. So let takes, there is a metal surface. So in metal surface, this is a metal surface, electron is going to collide, right? Okay, one electron is going to collide. Okay, there is several atoms, because metal actually, any element is actually constructed by millions of atoms. So let's say there is one atom. Okay, there is a nucleus, there are several orbits. We know from this Bohr atomic model, atom looks like this. Now X-ray is, and in this orbits there are electrons. Here is electron, electron. These are electrons resides in the atom. Now one electron is coming outside. Okay, this is electron from the cathode ray. Okay, and it collide with the atom, and after collision it also emits from the atom. So this is the case. When the electron is coming, the velocity, the kinetic energy of the electron is k0 or k0. After collision, let's say it changes k0 by del k. Due to the collision with the atom, what happens? The energy, the kinetic energy of the electron decreased by del k amount. This amount of energy will convert it into the photon. That photon is actually photon of a X-ray. That's why the X-ray is produced. So what is the case? How the X-ray is generated? When electron is bombarded with the metal, metal has many atoms. That means X-ray is actually collides with the atom. While this collision, the energy of the X-ray will decrease. If there is two classical particles, let's say two buses are there, then if it collides, then what will happen? The energy will be decreased, right? That is the case. The electron is colliding with the atom, and after collision, the del k amount of kinetic energy decreased. So it had the energy k0. Now it will have the energy k0 by delta k, and after that the electron is leaving from that atom. This is the case. Okay. Again, it may go through other collisions as well. I am coming to that later, but for the first collision, this is the case. So now the del k amount of energy decrease. So if the del k amount of energy decrease, this energy is converted to the photon. That photon is the photon of X-ray. That is actually reason behind the producing the X-ray. So this is the energy. So this should be equals to hc by lambda. This lambda is actually the energy, the wavelength of that photon, or the frequency, the wavelength of the X-ray. So del k is the, so from here we can write that lambda equals to hc by del k. Now if the total energy, the k0, is totally converted to the X-ray, as I discussed in the last part, if it is the case, the total energy is converted, then what will happen? The wavelength will be minimum. That means the energy of the X-ray will be maximum, energy of the photon will be maximum, which means the frequency will be maximum. That means the wavelength would be the minimum. That means lambda mean should be hc by k0. When the total kinetic energy is converted, then that will be the case, then the wavelength will be the minimum. So this is the lambda mean. So this lambda is obtained. So in this graph, this lambda mean, this is the lambda mean, this is actually hc by k0. This depends totally on k0. What is the k0? K0 is the kinetic energy. What is the kinetic energy? EV. It should be the kinetic energy. So this is the kinetic energy. So lambda mean should be hc by EV. We know this. We already know this. Okay. So now after one collision, let's say there is another one atom. There are millions of atoms, right? So after one collision, it goes another collision with another atom. So in that case, it enters with k0 minus del k kinetic energy, and it goes k0 minus del k minus, let's say, del k prime. So in that case, del k prime, this amount of energy will convert it into the X-ray photon, so it will be the lambda. So lambda will be hc by del k prime. So there are several collisions are there. So we can say we will have all kind of lambdas because there are millions of collision, millions of del k are there. So millions of wavelengths will be emitted. Again, there are not only one electron is bombarded, right? Cathode ray is flow of electron. So you can expect that lots of electrons colliding with lots of atom, not one time but several times. So there are huge number of collisions are there. For each collision there are certain amount of kinetic energy drops. So that energy is not actually predetermined, that is arbitrary, that can be anything, del k. Okay, and that energy is converted into the photon of the X-ray. So that X-ray can have any kind of random wavelength it can have. So that's why photon of the X-ray can have any wavelength, though there is a lambda minimum. That is obviously the case because the wavelength cannot be smaller than this, because if the total energy is converted in one collision, then obviously del k can have maximum value k naught. So lambda min is constant, that is hc by k naught, but after that any kind of lambda is possible during this collision. So lambda min is there, but that's why all lambda we can say will be present there. That's why we obtain this continuous spectra. This is that continuous spectra. That is a lambda minimum, but after that all kind of lambdas are there. Now intensity can vary, but this is also you can say more or less constant. But intensity is we can't say, but all lambda will be present there. That is the source behind this continuous spectra. Now coming into that, what is the reason behind these two special peaks? Why there are two special peaks? That is because, let's say again we have to draw this figure. When electron is passing, the electron from the cathode ray is passing through this atom, there are electrons in the atoms as well. So let's say in k orbit there are electrons. We know in k orbit there are maximum 2 electrons can be there. So these are the electrons. What can happen while passing through this atom? This electron can be kicked out by that external electron. Okay, so this was the electron k naught. This is, let's say, k naught minus delta k. This delta k will convert it into the photon, but this electron is emitted from the atom. That's why what will happen, there will be a vacant spot. There will be a vacant spot in the k orbit. Then if there is a vacant spot, then what will happen, the electrons from the higher orbit will come to fill up that vacant position. So now from Bohr hypothesis we know, let's say this is k, l, m, n and so on. This spacing should not be like this, okay, n, o. So now if there is a vacant spot in k in vacant spot, then one electron will come from the l or m. It can be the case. Also electron can be kicked out from the l orbit. This is k, l, m, l orbit. Then also electron can come from n to l or m to l. So this transition can occur. So this type of transition can occur, and due to this transition the photon will be emitted, and that photon will be the photon of X-ray. You have to understand that any kind of transition can occur here. Okay, there is no restriction to the k or l orbit, right? Electron can kick out electron of the atom kicked out by the cathode ray, electron of the cathode ray from any orbit. It can be k, l, m, n, it can be any orbit, and to fill up that position electron can jump from the higher orbit. It is the case. It may be from n equals to 7 to n equals to 2. It may be from n equals to 6 to n equals to 5. Any jump can be there, but all jumps will not have the same energy gap. This energy gap is quantized. We know from the Bohr's atomic theory, right? As these energy gaps are quantized, so the corresponding wavelengths are also quantized. So any wavelengths will not be there. So there will be many transitions due to this collision, but all wavelengths, wavelengths corresponding these two transition, all wavelengths for this transition will not be caused to generate a photon of X-ray. Okay, these four transition mainly from N to L, M to L, and L to K and M to K. These four transition, these energy gaps between these energy levels, these transition actually generate the photons of the X-ray. So that is the case. That's why you are taking these four special transition. So that's why there are some specific peaks. This is the reason. Okay, so the peaks for this transition, when this transition occurs, this transition occurs, one X-ray is coming out. Okay, and this X-ray has the energy, some kind of energy. That energy should be equals to K minus L, L minus K. Sorry, what will be the energy? EL minus EK. This will be 1 E1. There may be EM minus EK. Let me draw it, not here. Okay, so what will be the energy here? EL minus EK. For this transition it will be EM minus EK. For these two transition it will be EM minus EL, and this is EN minus EL. These four energy gaps, the wavelength corresponding these four transition, are actually remains in the X-ray range. Okay, there are other so many transitions are there, but this transition specially remains in the X-ray range. So these four transition actually give the peaks in the X-ray spectrum. For that transition, del E equals to EL minus EK. That will be Hc by lambda for specific lambda, right? So this is actually this peak is called the K alpha peak. Okay, and another transition, this peak is called K beta peak. As we see here, there are two peaks, right? K alpha and K beta. So these two peaks are there due to these two transitions, K alpha peak and the K beta peak. Okay, no, why the K? Because it's coming in the K orbit. So here there are two more peaks. This is one peak as well. So this peak is actually L alpha peak, yes, and another one is this is L beta peak. So four peaks will be there, but we can see here only two peaks because intensity of other two peaks is very less. These two peaks has the very less intensity. That's why it's not easy to visualize in the spectrum. But there will be four peaks due to this four transition. So that's why these peaks are called characteristic transition, because this purely depends on the metal, which metal you are using. Because these energy levels, this energy we know from Bohr's atomic model, this actually minus 13.6 by N for hydrogen atom, but for other atom this is not fixed. This depends on this energy levels, depends on the nature of the atom. So it varies from atom to atom. That's why the energy level varies and energy gap will also vary. So these peaks are not fixed. The position of these peaks, K alpha, K beta, L alpha, L beta, are not the fixed. This depends on the atom. So that's why this is called characteristic peaks. This depends. This is the characteristic features of that particular metal or the element. Okay, so we can identify what is the reason behind this characteristic nature. We'll discuss in the next class. The Moseless experiment, very important experiment. So that reveals the reason behind why this nature is there. What is the reason behind these peaks? What is the characteristic reason behind these peaks? That is actually the atomic number. So we'll discuss in the next part in the Moseless experiment. So in this part, in this class, let me stop here. So in this total class, we discussed first what is the X-ray, how the X-ray was obtained by the Röntgen during the experiment using the cathode ray, then the properties of X-ray and how the nature of the X-ray was determined, that it is a wave and the wavelength is very small. Then we discuss about the frequency and the wavelength of the X-ray. There are two types of X-ray are there, soft X-ray and hard X-ray. Then we discuss the uses of the X-ray. Then we discuss the X-ray spectrum, the continuous X-ray spectrum and the characteristic X-ray spectrum. And in the next class we will continue from here. We will discuss the Moseley's law, and then probably this chapter will be completed. So thank you for paying attention with me. So let's meet again in the next class. Thank you.